Good morning, everyone. I'm G. Sagastan from the Database Exploration Lab at the University of Texas at Arlington, along with Suraj and Professor Gautam Das. This work was done in close collaboration with Muhammad and Professor Sanjudi Basu Roy from the Big Data Analytics Lab at the New Jersey Institute of Technology. And we present our work, a generalized approach for reducing the expensive distance calls for a broad class of proximity problems. For the benefit of the audience, we would like to give you a broad and a brief introduction about proximity problems. These are the problems which involve estimation of distances between pairs of objects so that we can organize these objects based on their proximity. Classic examples are minimum spanning tree, clustering algorithms, and k-nearest neighbors. All of these algorithms involve the distance of notion between pairs of objects. So here we try to establish the notion of distances between pairs of objects, like by taking some real life examples and their relationship with other objects in the universe. So with the help of some real life example, let us try to establish the notion of distance between pairs of objects. On the top, you can see there are two cats which almost look alike. So the distances between them is really low, which also means that they are really similar. But at the bottom, you can see two dogs, which are from a very different breed. So the distances between these two dogs might be a little bit higher than the distances between two cats. But on the other hand, if you look at the toy balloon, the distances from either of these cats or from the dogs to these toy balloons are going to be really high, something like closer to 1, because they are totally different. Coming out of the abstractness of these cats and dogs and having established the notion of distances, let's take a real web-based application such as maps. So on a map, you might have to find the minimum spanning tree of the map. You might have to find a tour through the roads on the map. So there are numerous applications such as Google Maps API, Bing API, and Waze API, which helps you to find out these distances and map out the tours. So here, one of the more classical example is the reverse image search, wherein you use some sort of search engine in order to query for some image and to find out images which are very similar to it, such as in Google image search or Bing image search or Yahoo image search. Along these lines, in medical field, there are very important applications wherein you need to compare two particular images such as CT scan or MRI scan in order to find out if there is an existing problem for a particular patient. But what are the problems in proximity problems that make it really hard? There are two of them. The primary of them is the cost of the oracle. These oracles are not free, they are not cheap, they are very expensive. Second, all the distances in our work, we consider them to be obeying metric properties, so the distances can't be unlimited. But are these challenges really challenges? Let's take the example of Google Maps for the time being. So let's try to take the distance oracle cost from Google Maps API. As you can see, for the dynamic maps, for each of the 1,000 requests, you have to pay $7. Imagine the case of having a third-party tour maker, or for example, a gamer who has to go through this challenge in order to do this thing. So we assume that our distances are in the metric space, and we would like to explore what are the properties that are required for this distance to be in metric space. First, if you measure the distance from an object to itself, that's going to be 0. If you measure distance from an object hat to a rabbit or any object that matter, it'll be the same as the distance measured from the rabbit to the hat. And third, and the most important property is if you have the distances between any two pair of objects, that will be lesser than the sum of the distances between the objects and a third object. So this is the triangle inequality property. Thus, the overall objective of this project is to reduce the number of distance calls at the expense of local CPU computation and with leveraging the information about unknown edges and the relationship between those objects with other objects. For this purpose, we closely analyzed the proximity problems, and we found a very unique particular property all across proximity problems, which is ubiquitous nature of if statements. So for example, you can see in all of the proximity problems, you do take some action based on the distance comparison between pairs of objects. If the distance between a pair of objects and another pair of objects is greater or lesser, you do something or you do something else. So classic example is an MST or k-nearest neighbor, etc. For a better understanding, let us take a running example of 7 objects. In this, you can see some of the distances are known through the distance lookup, and some of them are not known. For example, distances from 1 to 6 is not known. And these are the distances that proximity algorithm needs to look up if it has to make a decision in order to uh, do an MST on it, or if it has to do a clustering based on distances. Before we go into solution framework, we wanted to introduce a novel formulation of the problem that has never been studied before, which is the direct feasibility test, which is introduced in the light of system of linear inequalities. In this, all objects and the distance between them, whether it is known or unknown, is represented as variables and constraints in the system of linear inequalities. For example, if you wanted to evaluate something like distance between O2 and O6 is less than or equal to distance between O3 and O5, you have a constraint represented like this. But most importantly, we turn it around in order to see if there is no feasible region for the other particular constraint that you have. If you do not have a feasible region, then you can successfully say that the distance between O2 and O6 is not going to be less than distance of O3 and O5, thus eliminating the requirement for a distance computation. As I said before, there's a novel formulation of the problem which has never been looked up and which involves system of linear equations, and then equation for the variables in the order of n squared, the equations for triangle inequalities in the order of n cube. And off-the-shelf linear programming solvers are expensive, so this works well and gives you the largest amount of savings than any of the algorithms that we know, but for scalability even to very small size graphs is not possible. We were very excited for the direct feasibility test, and it saves the maximum number of distance calls, but computationally it is not possible to scale beyond small settings. So we started looking at more practical graph theoretic based approaches. Before we introduced the solution framework in graph theoretic perspective, we wanted to give the viewer a brief understanding about the upper and lower bounds. So here in the given settings with a black hat, green hat, and a rabbit, you know some distances, which is 0.2 and 0.3 as shown. And now you can make an estimate about what are the possible distances between the black hat and the rabbit based on the triangle inequalities, which is 0.1 and 0.5. The 0.1 is called the lower bound, 0.5 is the upper bound. Thus, if you have many more objects where you know the distances with between the black hat and the rabbit, you can get better estimates about what these values are going to be. From all the lower bounds available, the largest one is going to be the best lower bound, and from all the upper bounds, the lowest will be the best upper bound. Earlier, when we were introducing the direct feasibility test, we said there is ubiquitive if statements everywhere in proximity algorithms. So we try to do one thing. So we try to reauthor these proximity if statements to incorporate upper and lower bound in saving the distance calls. How do we do it? So we reauthor the distance between OI and OJ greater than or equal to distance of OKOL. For that, we do if the lower bound of distance of OIJ is greater than or equal to the upper bound of OKL, do something. You do not call the distance oracle at all. And if you cannot do that, then you go ahead and do your distance computation as needed. Hey, here's the exactness genie. Exactness genie says, after the reauthoring, the answers that we produce will be the same exact as that of the answers produced by the vanilla algorithms. For example, in case of MST, it will be the same exact length of the minimum spanning tree, same clusters and intra-cluster distances in case of clustering, and same k-nearest neighbors. They are not limited to these three proximity problems, but across all proximity problems. Now, since we know that we can reorder the if statements in terms of upper and lower bounds, now the question is how to compute them more efficiently. Computing the upper bound for an unknown edge is far more easier because of the length of the shortest path. But for a lower bound, it is much harder. So let's take an example. So here you can see there are 2 points, x and y on the other end. So that's, you wanted to estimate the lower bound between x and y. But you know the shortest path from x to y, and somehow you know the shortest path from y to oj. The lower bound is thus computed as the distance, the residual distance of the wraparound that you can see in the bottom picture. You wrapped around the shortest path around an edge oi oj, and the residual is actually the lower bound. Thus, we try to formulate our problems as twin problems. First is a query problem, in which in response to a query, you wanted to find out what is an upper and a lower bound on an unknown edge. The second problem is, if somebody gives you a distance, some oracle has given you a distance in the graph, how do you update the data structure sufficiently so that for a new query for an unknown edge reflects these extra information that is added? So for estimating the upper and lower bound, there's a dynamic programming based solution framework which was proposed in 1990 by Sasha and Wong. In this, a particular node is taken, and for any pair of unknown edges, you try to see if there's a path to this particular point which kind of improves the upper or lower bound. It's a cubic algorithm and it's not practical for small or bigger size graphs. Understanding the challenges introduced by the cubic algorithm, as well as a deep understanding of Dijkstra's shortest path algorithm, we started designing a Dijkstra-inspired lower bound upper bound algorithm, which we titled as SPLUB. So here you can see there are two context cards, one is filled and unfilled, and you do not know the distance between them, and you wish to know the distance between them. So what do you do essentially is you run the Dijkstra's shortest path algorithm from both endpoints to all other objects in the universe. And you compute the upper bound by computing the shortest path between these two objects. But the lower bound is much more complicated, as I have explained before. So if you wanted to find out the distance between two contact cards, and essentially you know some of the distances, so you find the path, shortest path between the two contact cards which are filled on the left hand side, one's flap on the right, one flap on the left. You find the shortest path between them, and you find the shortest path between the contact card which is unfilled on the right side, which has a flap on the right and the left. So you know the shortest path between them from the Dijkstra's calculation, and there is a direct link between the bottom two contact cards. Thus, you can calculate the lower bound as the difference of that edge length and the sum of the shortest path lengths. And you do it for edges which are known to you. For example, you can see, you know the distance between the aeroplane and the knitting kit, and you do only for those kind of particular edges, thus reducing our computational overhead much lesser than the cubic algorithm that we had before. And we calculate it for each of the unknown edge, which of the known edges, and we take the largest of the lower bound and declare it as a lower bound, and the smallest among the upper bounds as the upper bound. Now you can see that this Dijkstra's space algorithm is much more simpler, and time complexity is exactly the same of Dijkstra's shortest path algorithm, which is simplest than log n. This can be used to answer the exact same answers that are produced by the order of n cube algorithm, and this scales to very large graph settings. We are very excited for the SPLUB algorithm, but the main limitation is it cannot be scaled to very, very large graph settings. So we started looking at the approximate solution framework as a remedy. So what do you mean by approximate LBUB schemes? So they produce bounds which are not as tight. So from the case of upper bound, it may not be as small, and in case of lower bound, it may not be as high as the tightest ones. So what do we gain out of this? We gain incredible scalability to very large graph settings. Exactness Genie is back, and it says the approximate results are for the upper and lower bound, and they're just for the bounds, not for the actual answers that it produces. And how do we do it? We do it at the expense of increased oracle calls. How do we make that possible? So you remember the solution that we have discussed earlier, Dijkstra's inspired solution framework, in which you calculate the distance, the shortest path from an endpoint of the unknown edge to a edge which is known, from the other unknown edge to the known edge, and then you subtract the distance out. So instead of doing that, we just took objects which are directly connected. For example, the contact card distance to the aeroplane is known from both of the contact cards. So for estimating the distance, you do the triangle inequality up here. So that is the difference that you have here. So now you can directly get that particular distance. So we call this more viable and more practical solution framework as tri-schemes, which involves triangles. So we use an adjacency representation for efficient query answering. So you can see that the distance between Acon and the knitting kit and the aeroplane is known, so they kind of are represented as an adjacency list. Now you wanted to find out the common endpoints. How do we do it? We kind of do it with the help of intersections. Intersections come to the heuristic, and it helps us in order to identify which are the common endpoints. Here you can see that Acorn and the contact card has a common endpoint, which is the knitting kit. Similarly, the aeroplane and the contact card has Acorn as a common endpoint. So we take such triangles in order to speed up the computation. Thus, in a very, very large setting, even this optimization of finding intersections faster may not work. So we relied on a binary search tree in order to make it really fast. So you can see the adjacency list on the bottom is transformed based on the distances as distance between Acorn and the knitting kit and the aeroplane, and then between between the knitting kit and the contact cards. This works very well in practice. The timings are amazing. For a lookup on an edge, it takes on an average order of m by n time. So there is theoretical results that we have proved in the paper. So please take a look at the paper for more understanding. Let's try to take a look at the datasets that we have used to validate our systems. So we have used SFPOI, which has 21,000 objects, and it has been used in k-nearest neighbor algorithms, clustering, and MST. Flickering is being used for k-nearest neighbor, which has 10k objects. UrbanGB is being used for 3 different kind of proximity algorithms and 360,000 elements. It is not always fun to say that our methods work well until you compare with somebody who is competitive. So we take 3 competitors here: ADM, which is the year-old state-of-the-art method that we have, and 2 other methods which gives you approximate answers, LESA and TLESA. So ADM has been explained previously as the cubic dynamic programming based approach. This algorithm calculates the upper and lower bounds using landmarks, let's say k of them. So you start with a random point, and then you try to find a node which is farthest from this, and then you try to find a node which is farthest from these both, and then you select k of them. And then for any pair of unknown edges, you calculate the distances through this landmark to get the upper and lower bounds. TLESA is basically an extension with a tree of this. Most excitedly, we want to give you the results portfolio. This is just a gist of the results that we have presented in the paper. So for more details, always please take a look at the paper that we have. First, let's take a look at the bounds which are produced by these algorithms: ADM, SPLUB, TriSearch, TLESA, and LESA. And we can see that the ADM and the SPLUB, as proposed, produce the exact upper bound and lower bound. TriSearch, LB, and when comparison with TLESA and LESA, you can see that the lower bounds are much lower and the upper bounds are much lower than the bounds which are produced by the other algorithms. Bounds are taken care of. Now it's time to take a look at the time for completing the MST. So basically, the results for other algorithms are given in the paper. Exactness gene is here. On the y-axis, you have the time taken for completing these algorithms. On the x-axis, you have the number of the edges in the given graph settings. This is for S of datasets. So the blue is ADM, the red is SPLUB, and yellow is tri-scheme. So you can see that for large settings, it takes more than 2.25 × 10⁴ seconds in order to complete these algorithms. For ADM, for SPLUB, it is roughly 1.25 × 10⁴, but tri-scheme is blazingly fast. You can not even see in this graph. They are super fast and almost finishes imminently. Bounds are taken care of. Time is discussed. Now it's time to take a look at the distance call save up by obtaining our very practical tri-scheme approach. So this is the exactness genie. These results are for the UrbanGB datasets for the PRIMS algorithm. So you can see we want to highlight 3 columns: tri-scheme, LESA, and TLESA. And along with LESA and TLESA, you see the percentage save-ups. And you can see that there is an increase in save-up as the dataset size increases. And this is going to be very high as and when the number of edges in the dataset increases. We almost save close to 1 million distance calls using tri-scheme when compared with LESA or TLESA, as you can see in the last column. So distance save-ups is very high using our practical algorithm tri-scheme. Thus, in conclusion, you have many more results for various proximity algorithms, what is priming, what are the drawbacks of competitive algorithms, proof of concept results, scalability results experiments, computational overhead, response to various parameters. All these things are discussed in great length at our paper. Please take a look at the paper. Thank you for listening to us. Bye.